The order of growth of a function's time that it takes to compute its result is a general category that the function falls in, such as linear or logarithmic. Two functions that use linear time might not take exactly the same amount of time to compute their result for the same input, but they both scale in the same way. The general shape of their scaling curve is both a line. And logarithmic functions all have that same characteristic logarithmic shape. And there are other shapes as well. Quadratic time describes a function that processes all pairs of elements in a linear input, or all pairs of values in a sequence of length n. So, for example, here's a function that computes the overlap between the elements in A and the elements in B by going through every element in A and every element in B and checking to see if they're the same. It adds a count when they are and returns the count at the end. So the overlap between 3, 5, 7, 6 and 4, 5, 6, 5 is 3 because 5, 5 are the same, 5, 5 are the same, and 6, 6 are the same. To compute this result, overlap compares all pairs of an element in A and an element in B. And that's a quadratic amount of work based on the input length. Here the input length is 4, and the amount of comparisons is 4 times 4, or 16. The amount of extra work required to process a length of 4 versus a length of 3 is this whole row. And therefore, if you compare the input size to the time it takes to compute the result, you get a quadratic shape. So here's what happens when we pass in n's from the range 20 to 200 and compute the median time required in order to return the result. 75 takes 2 milliseconds, whereas 150 takes nearly 8 milliseconds. And the curve slopes upward in a familiar-looking parabola. Another upward sloping order of growth is exponential time. Here things are even worse. A tree recursive function can take exponential time because the unmemoized fib function has to do 60% more work just to compute n that's 1 larger than the previous n. So computing fib 2 just requires this much work, fib 3 requires all this additional work, fib 4 requires all this additional work on top of fib 3, and fib 5 has to compute not only fib 4, but all of this additional work as well, assuming we don't memoize. So a tree recursive function like this, without memoization, will take what's called exponential time. Here are the common orders of growth that arise when analyzing functions. There are others, and there's also a formal system for analyzing functions and proving what orders of growth they belong to. But we'll defer all of that for a later course, and instead focus on understanding what these categories are and what their implications are on the runtime of a program. All of them describe how time scales with input size, and all of them describe general trends as opposed to the details of exactly how many microseconds it takes for a function call to return. So exponential growth is really slow, quadratic growth is slow but common, linear growth is very common, logarithmic growth is great and scales to really large inputs, and constant growth is the best of all. That happens when the input size doesn't affect the time. For example, in Python, the number of elements in a dictionary does not affect how long it takes to look up a value by its key. How that works is a topic for a later course, but the fact that it is a constant time operation to find a value by its key is an important property of Python dictionaries. Each of these categories can be described by a simple equation where we've written down the general time that it takes to process an input of size n plus 1 in terms of the time that it takes to process an input of size n, using some constants a and b to account for the fact that there are many details about how long it takes for something to run that we're glossing over as we talk about the general shape of time as a function of the input size. So for exponential growth, the amount of time it takes to compute the result for an input of size n plus 1 is something like a times b to the n plus 1, which, compared to the time it takes for an input of size n, requires an additional multiplicative factor of b. So that's the key characteristic of exponential growth. Incrementing the input size n multiplies the time by some constant. The bigger the constant, the worse this is, but basically for any constant, it's pretty bad. Quadratic growth is not quite so slow. Quadratic growth says that for an input of size n plus 1, it takes something like a times n plus 1 squared in order to compute the result, which, in addition to the time it takes to compute the result for size n, also requires an additional additive term. Now, adding to the time is better than multiplying the time, but still, the problem with quadratic growth is that the amount you add for just going from n to n plus 1 is a term that depends on n. So incrementing n increases time by n times a constant. Linear growth for a problem of size n plus 1 requires n plus 1 times some a steps, which, compared to solving the same problem for size n, is just an additive factor that doesn't depend on n. Incrementing n increases time by a constant. Logarithmic growth is the one that scales to really big N. Here we write down an expression for the time it takes to compute the result for n plus n, or 2 times n, is some constant times the log of 2n, which, compared to the amount of time it takes to compute the result for just n, adds some constant. So doubling n only increments time by a constant. If it's possible to re-implement some function in order to change its order of growth from exponential to linear by memoization, or from linear to logarithmic, as we did for exponentiation, that can substantially change not only the speed of your program, but the size of problem that your program can handle, without seeming like it's taking forever.